Hello, I'm Daniel Hogan with In-Q-Tel Cosmic Works. In this tutorial, we'll go over the basics of the Solaris Multimodal Preprocessing Library. This new resource makes it easier to do imagery preprocessing, that is to say, the sort of data cleaning and image processing algorithms that are a part of creating a data set for geospatial deep learning. This library makes the process easier by providing a set of building blocks from which elaborate image processing workflows can be constructed. The preprocessing library is one part of Solaris, the open source Python library for geospatial deep learning developed by CosmiQ Works. You can see the link on the screen there where you can download Solaris, and that link also includes instructions for installation. You can run it by creating a Docker container with the Docker file available at that site, or install it with pip directly from source code or from PyPy, the Python package index. Within the Solaris package are a number of sub-packages covering every part of a typical geospatial deep learning pipeline. This includes training neural nets and running inference with them and evaluating the performance of such models with standard evaluation metrics. But the part of the process that we're really interested in here is the very beginning, the creation of the data set for geospatial deep learning. Now, one important part of this is tiling the data, taking what are often very large images and breaking them into smaller pieces that are more amenable to being sent through deep learning algorithms. And if you have a set of data in the form of already ready-to-go imagery with accompanying vector labels, then maybe tiling is all you need to do to get your data set. And in that case, the tile sub-package will meet your needs. But often it's the case that one also wants to do more substantial kinds of image manipulation in preparing the data set. And that's where the preprocessing library in the preproc sub-package swings into action. Now, when I talk about manipulating the image, what kinds of things do I mean? Well, actually a number of different things. So for example, suppose that I'm creating a multimodal data set and I have data of one modality where the images are masked. I might want to take that mask and apply it to the imagery of another modality to achieve consistency between the two of them. But beyond just issues of masking or data filtering, and even beyond just cases of multimodal data, there are other times when I might want to process my imagery as an initial step. Really, any standard image processing algorithm falls into this category as well. So things like pan sharpening or noise reduction, for instance. In particular, analyzing synthetic aperture radar or SAR imagery is one area where these kinds of pre-processing algorithms are very important, because with SAR imagery, one starts with complex imagery. The value of each pixel is a complex number because it encodes phase information as well as magnitude. And getting from that kind of product to something that's more readily interpretable calls for a whole range of different types of algorithms that one might want to use. So all of these are the kinds of things that we're thinking about in terms of pre-processing geospatial data, and in particular geospatial imagery. So how does this pre-processing library in Solaris make the job easier? What the library provides is more than 60 Python classes, each of which carries out some distinct, well-defined data manipulation task. Now, these can all be useful individually, but their real value, their real power comes from the fact that they can easily be combined to build up user-defined classes to carry out image processing workflows of arbitrary complexity. So let's talk through an example of how this approach works. And for this slide, don't focus too much on the text right now. We'll actually revisit this example later in the tutorial. We just want to think about the big picture. Suppose that I have in mind a flowchart describing some pre-processing workflow that I want to carry out on my geospatial data. Maybe it looks like the flowchart here, which happens to be a pan sharpening algorithm. If I want to take that idea in my mind as expressed in the flowchart and turn it into a Python class to actually do the calculation, I can do it with this preprocessing library in 2 steps. The first step is to create an object for each block in the flowchart, that is for each task that has to be done. And for all of the typical types of tasks, classes to do them are already available in the library. So standard things like load an image, apply a mask to the image, do some calculation with the bands in an image. For things like that, and many other common sorts of tasks, the code is already there in the library, and one can always add additional classes if necessary. That's step 1. Step 2 is that I need to tell the computer how all these different tasks relate to each other, how the input and output of all the different tasks go together in the actual construction of the flowchart. And with the preprocessing library, I can do that in a single line of code using a concise notation to describe the relationship of all the different tasks with their various inputs and outputs. So let's look at each of those 2 steps in a little more detail. Step 1 is, as I said, creating an object for each task or each block in the flowchart. The options for doing so come from a pretty extensive menu. Here's the list of all of the classes that are in the library, and they're thematically organized into 5 modules. The first module, pipesegment.py, contains a base class, also called pipesegment, from which all of the other classes in the library inherit. This is what allows them to work together. The pipesegment module also contains some special classes that operate on other classes for doing certain kinds of very complicated things, but in a typical use case, none of that is required. Within the image.py module, one can find classes related to manipulating geospatial imagery of any kind. And then the optical.py module, which is pretty small, just contains a few classes that are really only useful for optical imagery, whereas the sar.py module is more developed, containing a collection of classes for doing the special image processing related to working with SAR. Finally, the label.py module contains classes for working with vector labels and other kinds of data that can be expressed as text. So defining an object for each block in the flowchart, in practice, almost all of which will be things that are already available right here in the library, is the first step. And the second step, as I mentioned, is to tell the computer how they all connect together using this special notation. The line telling the computer how to connect the different blocks together uses just 2 symbols beyond the names of the variables themselves: a multiplication symbol, that is a star, and an addition symbol, that is a plus. And the star is used for pipelines. So by that I mean cases where the output of one object is sent into the next object, and then its output is sent into the next, on down the line. So I can denote that as shown in the top line here using the star. So for this slide, assume that F, G, H, A, B, and C are all objects of various classes from the previous slide. And then F star G means to tell the computer to take the output generated by object F and feed it in as the input to object G when it's doing its calculation, and so on. But not everything that one wants to do is a simple one-dimensional pipeline like that. Sometimes a workflow calls for branching. So by that I mean cases where the output from one task is fed in as the input to multiple tasks, or the output of multiple tasks is all brought together to be used together in one place as the input to some single task. And anytime I'm doing that, I can describe that situation to the computer with this notation with a plus sign. So for example, suppose that C is some class that takes two inputs to be fed into it, and A and B are two other classes that respectively generate those two inputs. The notations shown on the second line here is how I would describe that situation to the computer in my line explaining the connection of all the different tasks in the workflow. Now this is starting to get pretty abstract. So let's look at a real world example to see how this happens. And the first example that we're going to look at is the case of taking an image with both optical bands and a near infrared band and calculating the normalized difference vegetation index, or NDVI. This is a measurement that shows where the plants are in an image. And whenever setting up a workflow for pre-processing data, I think it's helpful to start by visualizing the flowchart of what one wants to do. In this case, there aren't too many steps. We're going to start by loading in the sample image. We're going to compute the value of the NDVI, and then we'll take that data and save it to disk as a new image file. So those are the steps, and here's the code that does them. You can see that in this code, 3 objects are defined, one for each block in the flowchart, one for each task to be done. The load image class in the image module, not surprisingly, loads in my sample image from the disk. Save image in the same module saves the output to disk. And sandwiched between them, we have an object of the band math class, which does some calculation with the bands of the image. Now for the NDVI, the way it's calculated is it's the difference of the near infrared and red bands divided by their sum. And in this particular sample image, those happen to be bands 2 and 3, or 3 and 2, respectively, which is why we have the formula here. The 0.1 is just to prevent division by 0 in there. So I've defined one object for each of those classes, one object for each block in the flowchart, and you see they're connected to each other by stars. That's where I'm telling the computer the structure of this thing. I'm telling the computer how they are related to each other to create the flowchart. Now this whole first command creates an object that describes the calculation that I want to do. Well, it's actually a linked list of objects, but for our purposes, we can think of it as just one. And at this point, having run this highlighted line, the computer now knows what calculations to do, but they haven't actually happened yet. The calculations actually happen in this next step where I call the object that I have created. So did it work? Well, in this case, to see if it worked, I can just look at that output image and see if it's what I'm expecting. But often, if I'm trying to do something complicated, I might want to look at some intermediate result from somewhere in the flow chart, just to make sure things are going the way I expected, or maybe to do some debugging. And so to help out with that task, there are a couple of classes that are very useful. One is the show image class, which will print the image passing through the pipeline wherever in it I insert this class. And another is the image stats class. Those are both in the image module, and in the case of the image stats class, it prints some descriptive statistics. Both of these classes, whatever input they get, and send the same thing through unmodified as their output, which means I can stick them anywhere in my workflow that an image is passing by, and they will not affect the calculation. They'll just provide this information to the screen. So now when I call the object with these additional classes stuck in there, it puts things, and it looks pretty good. So this was our sample image. It's a nice little roundabout in Rotterdam, the Netherlands, some surrounding area. And here is the NDVI. You can see it's bright white everywhere that there is vegetation in the original image, and it's gray with a few black pixels mixed in everywhere else, which is what we wanted. Now, in this example so far, I've just created a single object to do the calculation. And sometimes that's all that I need, but often I want to be able to repeat the calculation many times. For example, maybe I have hundreds or thousands of image tiles, and I want to do the same thing for each one of them. To do that, the best approach is to create a class. And here's an example of doing that. This code runs the exact same process that we've just seen, but now it's in the form of a class that I can easily reuse. So here in the class constructor, which by the way takes the input and output file paths as arguments so that I don't have them hardwired into the code, which would not be good for class reusability. Here in the constructor, I do the two steps, and here I've separated them out. So the first step is creating an object for each block in the flowchart, loading the image, calculating the NDVI, saving the image. And here at the end, I have my statement telling the computer how they all relate to each other using those stars. And then down here in the body of the code, once I figured out what the paths are to the input and output, I create an instance of my class, and I call the instance, and then the calculation happens. So this is an example of creating a user-defined class to do my calculation. One of the nice things about creating a class like this is that the class that I create also inherits from the same base class as all the things in the preprocessing library. So this class that I've made is just like the classes in the library. I can use it to build up some even more elaborate workflow in the future. In this example, however, we had a single pipeline, and sometimes that's enough, sometimes it's not. So let's look at that pan sharpening algorithm that appeared briefly on the screen before. Pan sharpening is a process where you take a low resolution color image and a high resolution grayscale image and combine them to create a high resolution color image. And here is one way to do so. For the purposes of this tutorial, it's not important to understand the details of what's happening here. And it's actually also not important that this is not the world's best pan sharpening algorithm. There are better things out there. But this will do nicely for illustrating how to handle cases where data is branching apart or coming together. So this is what we want to do. This is the flow chart that we start out visualizing in our mind, and here's the code to make it a reality. Just like before, we have one object for each block in the flowchart. So load the image, resize it, change around how the colors are expressed, all these different steps in the process. And the important part is this last line. Well, it got a little long, so I wrapped it around to the second line. Maybe we count that as two. But it's one Python command in any case. which is what tells the computer how all those operations are connected. It's what tells the computer the topology of the flowchart. And the thing to notice here is these plus signs, which describe how the data is branching apart and coming back together. Let me show you one example of this in action. So I'm scrolling back up to the flowchart, and let's look just at this middle part of the process right here. So what's happening here is that we have this command, and its output is used in two different places. It's used here to just pull out two bands from the image, and it's used here to do a calculation with two other bands of the image. Finally, both of those results are combined by stacking those bands together to make a new image down here. So we have the flow of data splitting apart and coming back together in this one area of the flowchart. So let's see how that happens in the code. Here's that first object, the output of which is used in two different places, and it's followed by an asterisk indicating where its output is getting piped into. But instead of being sent to a single object, it's being sent to this sum, indicating that it will be fed into getHS, which is the object on the left that we saw, and getV, which is the block on the right that we saw. Finally, both of their outputs get sent to the same place. So if you think of this as sort of like the distributed property or something, both of these get sent through this asterisk into the same output. So with this class, I added some show image classes inside of it so we can see what's happening. Here's the original color image, pretty grainy. You can probably see the individual pixels, or at least be aware that it's not too smooth looking. And once it's combined with the high resolution grayscale image, which is not shown, here's the final result, and all the details are very sharp. While we're on this example, let me mention one more advantage of creating one's own class. Because each user-defined class inherits the properties of that pipe segment base class, one of the things that they inherit is this method called parallel. And if I do want to use the class many times over many tiles or whatever, then I can use this method, and it will do the work of running over the different input images all in parallel. So for example, if I have a multi-core computer, it will use all of the cores of the computer instead of using just one of them serially to go through the images one by one. We're going to look at one more example after this, but before we do, I want to say a little bit more about this notation, because it's actually more generalizable than one might think. So here's a pretty tricky example. I designed this one to be tricky. So the output of operation A, or the output of block A in the flowchart, is fed into two different places, B and C. But after that, we don't just have two separate pipelines running independently of each other. Instead, we have this case where the string of calculations on the left isn't just an isolated pipeline, because it depends on all these intermediate results coming over from this string of calculations on the right. So we don't just have two clean separated pipelines, we have this whole web of stuff going on. And that raises the question, can the notation support even a complicated arrangement of calculations as shown here? And the answer is that yes, it can. So for these tricky cases, I like to start at the end of the flowchart and work my way back to the beginning. In this example, there are two blocks in the flowchart, the output of which is not used anywhere else. Those are F and G, so I'll start with them. Now what I'm going to do is iteratively go through the expression that I have, and for each object, say where it gets its input. And in that way, I'll work my way back to the beginning of the flowchart. So starting with object G here, I can see that it gets its input from object E. So the way I show that is with the star, indicating that the output of E gets piped in as the input of G. Now, what about object F? Well, it gets its input from two places, D and E. So the thing to the left of its star isn't going to be one variable or one object. It's going to be both of them. And if F cares about the order of its two arguments, which most of the classes do if they require more than one, then I do want to get the order right here. So maybe it needs to be E plus D, just depending on which of these classes make which arguments for feeding into F. Okay, so at this point, I've explained the input of G, I've explained the input of F, but in doing so, I've added some new objects to the expression, and I need to say where they get their input. Well, E gets its input from block C. E appears two places in this calculation, so I could actually define its input at either one. I could tell the computer that E gets its input from C there, or I could tell it here. It doesn't matter. I could even say it redundantly at both places, although that's extra typing that does nothing to improve clarity, so I'm going to choose not to do that. D gets its input now from B and C. So just like before, I'll put that in. And finally, B and C both get their input from A. So I could show that for them separately, like that, or since B and C are already paired together with a plus sign, I can just feed A into them both very concisely like that. So as you've seen, there is more than one correct way to write the notation to describe a given flowchart in most cases. And even though this was a tricky case, and even though we stopped along the way to consider different ways in which we could write it down, type-out was still faster than even it was to draw this flowchart when I was preparing these slides. So for the final example, I want to show one case where this approach can be very useful, and that is when working with synthetic aperture radar data. So if you don't work with SAR or have never worked with SAR before, you can tune out for just a couple of minutes here. If you have, then you know that a typical pipeline for going from complex SAR data to magnitude data might be something like this. Load in your complex data, apply some scaling factor that you pull out of the imagery's metadata, calculate its intensity, do a multi-look filter to help contain that salt and pepper pattern, convert the intensity from its raw value to being expressed in decibels, orthorectify the image so you get from range azimuth coordinates to some standard coordinate system that you can work with using data from other sources, and save the result. And with the preprocessing library, all of that's very straightforward because the SAR module contains classes to do all of these tasks. So you can build a class to carry out exactly that pipeline. Here's some pictures. The raw intensity and even the intensity after doing the multi-look filter don't look like very much because the imagery magnitude varies, the imagery intensity varies over orders of magnitude. But once I convert to decibels, I can see that there really is a picture there. And then I can orthorectify it to get my final result to save. With SAR data, Working with magnitude is very useful, but sometimes one also wants to make use of information contained within the phase of the SAR imagery. And there are different ways to do that. One way is with polarimetry, and the library includes several classes for different kinds of polarimetric decompositions to do exactly that. Here's the output of one example. When one is generating a multimodal data set using SAR data and optical data, for example, one might have a mask on the SAR data because it's some smaller strip, and the optical may cover a larger area. And so a very common task for the preparation of such a data set is taking the mask from the SAR and applying it to the optical to get them to match. The original motivation behind the preprocessing library was the creation of the SpaceNet 6 data set, when we had to do all sorts of things like this. And so the idea behind the library is to make it easier to do exactly these kinds of things in the future for creating these kinds of very complicated data sets. So for a few concluding thoughts about all of this, the overall design is to move as much of the mundane work into the background. And pipe segment base class that underlies the whole preprocessing library does a lot of the work automatically. So for example, when preparing a data set in this way, the user doesn't have to keep track of all the different file paths where different intermediate or temporary results are being stored. In fact, the software takes care of that. The intermediate results are stored in RAM, and they are deleted from there just as soon as they are no longer needed. The user doesn't even have to figure out the order in which to do the calculations. Once the flowchart is specified, the computer figures that out too. So the user's only job should be to declaratively state what computations they want to be done, what data manipulation they want to be done. And the mundane details are a job for the computer. This approach of building up the workflow can be used with any type of data. The classes in the preprocessing library, of course, focus on geospatial imagery, and we have a special affinity for SAR, but this is a very general approach which can be used with all kinds of geospatial imagery, and more broadly with any kind of geospatial data, or even with any kind of data at all, if one is willing to write any necessary supporting classes that aren't there already. But for these typical geospatial use cases, all of the most commonly needed classes, for the most part, are there already. And then finally, this approach of taking smaller pieces and building up workflows of arbitrary complexity allows for handling jobs of any size. If you'd like to learn more about this, I would encourage you to look at the documentation at solaris.readthedocs.io. In particular, if you go to the page shown on the screen and scroll down to the very bottom, you'll see links to the 3 tutorials on the preprocessing library. These are the documents that we skimmed over in the course of this tutorial, mostly just looking at the figures and some of the code snippets. But if you'd like to learn all of this in greater detail, I encourage you to go back and really read through those and see all the different things that can be done with the preprocessing library in Solaris. Thank you for listening.